Hello everyone, my name is Adrienne. I'm a PhD student at the Future Industries Institute at the University of South Australia. Today I'll be presenting a small part of my PhD, which is focusing on using zircon chemistry for iron oxide copper gold deposit targeting. This project is affiliated with MinEx CRC, in which I'd like to thank its participants and also affiliates. I'm doing this project to address a current problem in today's mining industry, where with the increase in population, technology, and general standards of living, an increase in our deposit discovery is necessary to meet growing global metal demand. As you can see in this figure showing gold and base metal discoveries over the last century, the rate of deposit discovery is gradually decreasing, and the majority of the deposits at the surface have already been found. As a result, we are being forced to explore in deeper terrains to find these deposits, which come at an increased cost and risk. Currently, a lot of exploration programs mainly use geophysical techniques to target areas at the surface, or that are buried by thin or shallow cover sequences. However, these techniques are dampened when you are applying them to areas with thick cover sequence. Consequently, there's been a shift towards understanding how the cover may be used to maximize the recognizable footprint of mineralizing systems through understanding their geochemical signatures and how they may be transported into the overlying sedimentary cover. This is particularly important in South Australia, where a large portion of the region is overlain by a thick cover sequence. To address the current exploration climate for iron oxide copper gold systems, we've focused on one accessory phase to use as an indicator mineral, which is zircon. It was important that this phase was abundant and grew in different environments, that it was sensitive to its environment to record any changes it was subjected to, and lastly, that it was a resist state phase, so that it could withstand any physical and chemical weathering associated with the transportation of this phase into the overlying cover. Multiple studies have reported geochemical criteria using zircon for porphyry systems. However, minor work has been done at looking at them within iron oxide copper gold systems. What we want to know is how the chemistry of zircon changes depending on where it is located within a mineralizing system. Whether the zircon is located within the mineral deposit itself, in the associated alteration halos, or if they are completely unassociated with the mineralizing system. Through understanding this, we will be able to establish our geochemical criteria using zircon. Additionally, through investigating zircon above a known mineral deposit in the overlying cover, we will be able to determine if zircon preserves geochemical signatures and if those signatures are kept when zircon is translated into the overlying cover sequence. This will address our current problem with future deep exploration. Today I'll be showing you some results from my background study, which is looking at zircon from unaltered igneous suites in the Gawler Craton. We will then be focusing on comparing this data to zircon from altered samples within the Gawler Range volcanics and the Hilltopper Suite. The Gawler Craton in South Australia is a prime study area, as the majority of the mineralized basement rocks are overlain by a sedimentary cover sequence that can range in centimeters to hundreds of meters in depth. The region hosts some of the largest iron oxide copper gold deposits in the world, which include Olympic Dam, Prominent Hill, Carrapateena, and Hillside. This hydrothermal event was associated with the emplacement of the Gawler Range volcanics and the Hilltopper Suite, with some copper gold mineralization residing within the Donington Suite, St. Peter Suite, and Sleaford complex. Minimal work on zircon chemistry has been undertaken in the region. Therefore, it's important to first establish the background. The background chemistry of zircon will be established through analyzing zircon from these igneous suites that are unaltered. From these samples, what we want to understand is how the chemistry of zircon vary between the units in order to use this background as a foundation for future work. LA-ICP-MS geochemical data was collected from zircon from each igneous suite, with minor differences in chemistry evident in these ratios on the left when looking at the 25 and 75 percentiles for each igneous unit. These ratios best separate out the Donington suite, GRV, and Hiltipur suite, which is seen in this bivariate plot on the right. The Hiltipur suite zircon are enriched in europium over hafnium and niobium and tantalum over phosphorus ratios, where the enrichment in the Hiltipur suite is largely attributed to the zircon from this suite crystallizing later in the magma evolution, where trace elements, rare earth elements, and hafnium become enriched. When looking at how zircon chemistry changes when it's associated with alteration, we're only going to focus on two igneous suites, the Gawler Range Volcanics and the Hiltipur suite. These two suites are the first that come to mind when you're looking at iron oxide copper gold mineralization in the Gawler Craton, as they were coincident with the mineralizing event. Additional samples were collected from each suite that were proximal to mineralized areas, and that displayed variable potassic and iron alteration associated with the hydrothermal fluids. With iron oxide copper gold systems, potassic, sericite, and iron alteration increases with proximity to mineralization, which almost acts as a vectoring tool itself, and typically follows the arrow indicated on this diagram. Based on this, we've classified the zircon based on the degree of alteration present in the host rock, where zircon from unaltered samples are derived from the background study, and moderately and highly altered samples display increasing iron and potassic content. Based on this classification, we can see that principal component analysis show that zircon from the GRV display higher cerium, europium, thorium, and niobium content from altered samples compared to those from unaltered samples, with the best discriminating plot represented by cerium and phosphorus content. Zircon from the Hiltipur suite display clear enrichment in europium, titanium, and phosphorus in the PCA space, with the best discriminatory diagram seen on the bottom right, where zircon from unaltered Hiltipur suite samples are enriched in cerium, niobium, lead, tantalum, thorium, and uranium. Additionally, we can see that zircon hafnium content increases with alteration of the host rock. When looking at rare earth elements specifically, Gawler Range volcanic zircons largely overlap, with moderately altered samples having a clear enrichment. On the other hand, with the alteration of the host, zircon rare earth element decreases for the Hiltipur suite. This data was compared to the main geochemical plot used to discriminate between fertile porphyry suites, where fertile porphyry suites typically have high europium anomalies. Our data overlap with the porphyry data, where zircon display higher europium anomalies with alteration in the GRV, but the opposite trend is seen in the Hiltipur suite, where it decreases. As these zircon geochemical trends can be compared to the intensity of alteration of the host rock, we suggest that the hydrothermal fluids that are altering the Hiltipur suite plutons appear to be leaching trace and rare earth elements from zircon, and either redepositing these elements in other accessory phases in mineralized zones, or they're depositing it within the GRV zircon, which sit higher up in the system, therefore enriching their zircon. Additionally, the Gawler Range volcanic zircon could be enriched by the hydrothermal fluids itself, which are enriched in fluorine, uranium, chlorine, and rare earth elements. However, further research into the chemistry of zircon from these suites within the mineral deposits is needed to make a confident interpretation. Based on these results, a background on zircon has been established for the Gawler Craton, with minor differences between the igneous suites evident through these geochemical ratios. Additionally, zircon displays enrichments and depletions when associated with hydrothermal fluids, showing the potential of using zircon as a tool for exploration for iron oxide copper gold mineralization.